Let's take a look at binomials. So these look at the probability of a certain number of successes within a set number of trials. Bi stands for two options, either success or failure. And nomials is telling us that we're looking at success and failure for multiple trials. I did a small experiment here involving rolling two six-sided fair dice, or at least I think they're fair. And I did this a total of 48 times. Now I'm going to consider success rolling a 6 on a die. So if I'm thinking about what could happen here for this raw data, and data can get messy. So it might not line up to what we would get if we did a tree or a table. We're going to check that out. But when I actually rolled this, I got 0 to show up about 69% of the time. 1 showed up 29% of the time, and 2 showed up 2% of the time. And I used GeoGebra to get these results. I'm also seeing inside of GeoGebra that I got a sample average or a mean of 0.33 or so. So this means I expect to get about 0.3336s in 2 rolls. So I don't even expect in a given roll to get a 6. I didn't get any there. Although I do expect to get them sometimes. In fact, I'm going to get one about 29% of the time. There's still a fair amount of spread to this. So for the standard deviation for this sample, I got about 0.5191. Now, I don't know how close our sample data is going to match up to the reality of the situation. So let's take a look at a tree. So this is what I got for some real data. And we're going to compare this to some theoretical stuff. If I'm drawing a tree, each roll could be either a 6 or not a 6. I'm looking at 2 rolls, so this thing's going to go too deep. I'm using this little C here, complement, to mean not 6. So either 6 or not a 6. This first set represents the first roll. The second set here represents the second roll. And this is the theory for what should happen. Doesn't mean it's going to line up perfectly, but we might see that some things are close. In any given roll of this first die, I expect to get a 6 1 out of 6 times. It's one of the 6 sides. So that means 5 out of 6, the other sides, I'm not getting a 6. For my second roll, for my second die here, I'm expecting to get a 6 to show up 1 out of 6 times, regardless of what's happened for this other one. They're independent rolls. If there's a 1/6 chance of getting a 6, other 5 sides again represent not getting a 6. Now I'm going to count in this tree. At the top, you've got 2 6s in a row. 6 and then a 6. This spot here represents getting a 6 and then not a 6. This represents no 6 and then 6. That's 1 6 and 2 rolls. And this bottom one represents no 6 and no 6. That's 0 6s. So again, my possible outcomes here, I'm either getting 2 6s, I'm getting 6 on the first, not a 6 on the second. I'm getting no 6, but a 6, and I'm getting no 6 down at the bottom. To calculate the probabilities of these events, you multiply in the tree. So the probability of getting 2 is going to be 1/6 for the first times 1/6 for the second. I'm going to type that into a calculator to see what I get. And 0.02 7 repeating. So actually pretty close to what we were seeing for that data for 0.02. That's promising. To figure out the probability of x equals 1, I have to add these two different spots in the tree, starting with this first one, 1/6 times 5/6. This next spot here is 5/6 and then 1/6. So I have 1/6 times 5/6. I have 5/6 times 1/6. And combining these, I get that this is approximately 27.7% repeating. When I was looking at the raw data, I got approximately 29%. You know what? That's also pretty close. Finally, let's look at the probability of getting 0 6s. That's down here at the bottom. So that's 5/6 for the first. That's 5/6 for the second. I'm going to type this into a calculator. 5/6 times 5/6 and 0.694. This is actually surprisingly close to what we were seeing for that raw data. And that's promising already. So this means if we roll our dice enough times, sort of what we're seeing in practice should match up with the theory. That's promising. That's why we study the theory in the first place. Let's see what's going on with the expected value and the standard deviation. Expected value, I'm doing first x value times probability. I'm multiplying those things and adding them up. So I've got 2 is the first x value in my mini table here with the probability of 0.027 repeating, or 1 out of 36 if I'm writing that as a fraction. Next one of these, I have 1 times 0.277 repeating, or 10 out of 36 if I wanted to write that as a fraction. Finally, the last thing I have is 0. This looks like this is 25 over 36, or 0.6944 repeating if you're writing that thing as a decimal. And you can do that either way. For accuracy, I'm actually going to type in those fractions. You can try doing it with the decimals as well, just to see how close they are. Should be comparable. And when I did this, I got 0.333 repeating. Pretty promising, because that's also what we got from the actual data. I'm again kind of surprised by how close that was. I was just rolling dice. I want to find the standard deviation, but before I can find the standard deviation, I had to find the variance. Formula for the variance says take the first x value in the table, 2, minus the center, 0.33 repeating. Square that to take care of any negative issues. Multiply these by the probabilities and add them up. So this is just serving as a little bit of a review of some of these core concepts before we try to build on them. So first x value was 2, center was 0.333 repeating, squared, times that first probability for 2 was 0.027. Next x value was 1, center was 0.333 repeating, probability for 1 was 0.277 repeating. Finally, I had 0, 0.333, and the probability for this was that 0.6944 number. You can type this in using decimals or fractions. I'm going to type this in just how it looks. It would be better to use the decimals, and if you're comfortable, or to use the fractions, and if you're comfortable, I would encourage you to do so. I'm just trying this out to see what I get. And when I do this, I get 0.27 or so for my variance. Looks like our standard deviation is a little bit off here, but keep in mind that this is still your variance. You have to take the square root to get the standard deviation. Even then, it might not line up perfectly. That's kind of the way that this raw data to theory thing works. Sometimes it's close and sometimes it's not. If I take the square root of that number, I'm getting approximately 0.527. And you know what? Actually pretty good. 0.52-ish, 0.52-ish. I'm getting roughly the same result. Here's kind of the big picture for this and sort of why we might want to look at these things side by side. Even though you didn't see it, to get this raw data, I had to do 48 rolls of the dice and then type all that data into GeoGebra to get these numbers. In practice, the tree was much faster for me, even if it was a little bit messy. So I want to know, what would this look like for, say, n equals 100 dice? Well, if you're thinking about the tree, this is already getting pretty big at 2. If I was 100 in, this is going to be way too big for the tree. Other downside is I only have 2 dice. I would need to have like a big bucket of dice to roll this 100 times. And even then, I would want a lot of trials to type that inside of GeoGebra to come up with these values. So I'm seeing a bit of an issue. If I'm dealing with these larger values of n, it's too big for a tree, and it's too big to do in practice. Okay, but that's just 100. What if I wanted to study 8 billion people? Well, then I'm kind of at a loss here, because I definitely don't want to draw a tree or do some raw data with something that large. So I need to come up with a new system for calculating these sorts of probabilities for really, really large situations. Before I can do 100, though, I should really try to strive to understand just 1. And if I can understand the building block for just a single set of branches here, maybe I can find ways to kind of bootstrap this together to avoid having to do these large trees in the future. So that's my goal for today. I want to come up with some sort of a process that looks at these success and failures for large trials. Before we do that, we're going to build up our toolbox a little bit by looking at 2 very similar looking problems. Suppose there are 500 candies in a jar, with 40 of those candies being blue. If you draw 2 candies in a row, replacing and mixing between the poles, what is the probability of getting 2 blues? You could draw out the tree, but if you're looking for blue and then blue, if you replace, then for the first pole, there are 40 are blue out of 500 candies. You put that back in, you mix it up. So when you're multiplying this next probability, this next branch in that tree, it would still have the same number of candies, 40 out of 500. So I could type this into my calculator. I can even say 40 out of 500 squared. because this is just showing up twice there. I get 0.0064. Now let's consider what happens if you don't replace. This would be a tree that starts to get kind of messy because those probabilities would change as you pull out those candies and hopefully get to eat the candy as you go. Blue, blue. 40 out of 500 for the first pull are blue. But when you remove this candy, if you don't put that back in, you're going to have one less candy. And that candy in particular was blue. So for this next probability, it would be 39 blue, one less, and 499 candies, one less there as well. I have to be a little bit more careful with typing this into a calculator. 4 out of 500 times 39 out of 499. But when I do so, I get 0.00625 or approximately 0.0063. So 2 observations. First observation, be careful of changing probabilities. It's kind of nice when they don't change, when they stay independent. That's another way to label these. If your probabilities are staying the same for each of the polls, this is a situation where it is independent. If things change as you poll, then you would describe that as being dependent. So be careful of changing probabilities, but if I look at the final results, even though these setups looked pretty different, 0.0064 and 0.0063 are pretty similar results. So however, even though the probabilities change, the change looks minimal here. And since it's so small, I feel like I can really do the problem either way and get approximately the same answer. 0.0064-ish would have been fine as an estimate for both. And why is that? Well, if you think about it, if you only had 2 candies and someone took away one of your 2 candies, you would probably notice that. That would be a pretty large impact. That dependency would be massive. Now, if I had 500 candies sitting here, if you took one of those candies away, you probably wouldn't know it's missing. So the change here looks minimal. And the reason for this is if you have a small sample, if you take away a small number out of a larger population, the results look the same for independent and dependent. So when we're making these trees, if we're wondering, should my probabilities stay the same, like this nice tree that I had on this previous page, or should they change and get messier? Well, if you have a small enough sample and a large enough population, you may as well just do it for the nicer numbers. This is called the 10% rule. And this states, if you sample 10% or less of a population, you can assume independence. That's a pretty big win because checking independence can get kind of tricky and messy. So this independence is now just a way we can check with this 10% and vice versa. So assuming you have a small enough sample, you can assume independence between trials. That makes things pretty clean. So for example, if you sample 10 times from a population with 8 billion, I don't have to worry about changing my numerators and denominators in this case. 10 is a small sample from a large population. We can assume independence because we are sampling less than 10% of the population. On the flip side, let's say you sampled 40 times out of 200. Well, this 40 out of 200 is more than 10% of the population. And I know this because 10% of 200 would be 20. So this means if I wanted to do a problem involving sampling 40 times from a population with 200, I cannot assume independence. And I'd be dealing with some really, really messy trees. So I'm going to assume this to be true for what I'm going through today, because otherwise my trees are going to get so messy that I wouldn't even want to start that kind of a problem, especially if I had to go 40 branches in with changing probabilities. So I'm going to see that on this next page when I'm starting with just one sample, pretty small sample, out of hopefully a large population. So this is my building block to trying to understand n trials. So we start with n equals one single trial at a time. And we call this single trial a Bernoulli trial. This has two options. It's either a success or a failure. That's where that by part of the binomial is coming from. We say the probability for success is P. And we're going to call the probability for failure Q. There are only two options for Bernoulli: success or failure. And if you only have one trial, I don't have to worry too much about independence between poles. But even if I did, I now have a backup for this. I also can use the 10% rule to make sure that my single trial could really stand on its own. So this means that this thing is essentially repeatable. Repeatably the same. Suppose X is a Bernoulli trial. So that means it's success and failure, and it's only one trial. And P equals 1/6. So this is a probability of getting a 6 on that die. So this is the equivalent of looking at a single die roll and looking at the likelihood of getting a 6 for one roll. Let's calculate the probability of getting X equals 0 and the probability of X equals 1. Okay. Probability of 0 would mean no successes. This would represent a failure. And 5 out of those 6 sides on my die represented a failure. If I wanted to know what was the probability of success of getting a 1, that was a 1 of the 6 sides. So something you may notice, P and Q here, they add up to 100%. They're complements. So P plus Q is 1. Q is the opposite of P. Let's say I have a Bernoulli trial and P is equal to 0.5. Let's calculate the probability of 0 and 1 here. This is like looking at a single coin flip. It's either a failure if you get a tails, for example, 50% chance of that, or a success if you get heads, only 2 options, and my probabilities add up to 100%. So these would represent sort of the starting probabilities for how things branch off. I might also want to know, okay, how do I find the expected value and the variance for each one of these sets along the way? And how can I combine those or add them together? So let's say I'm looking at a single dice roll. The expected value, x values times probabilities, and you're adding them up, would look like 0 times 5, 6, plus 1 times 1, 6. 0 successes, probability is 5 out of 6. 1 success, probability is 1, 6. 0 times anything is 0, so that just goes away. 1 times anything is just that anything, so this would be 1, 6. If I want the variance, I'm going to take x values minus the average, square them, times their probabilities, and I'm going to add them up. So my variance here will be 0 for the first outcome, minus, and I just got an average or an expected value of 1, 6, so I'm going to put that here. And the probability of getting 0 was 5, 6. Next x value in my mini table here is going to be 1. 1 has a probability of 1, 6. So I have the value 1 minus the mu, still 1, 6, squared to take care of those negatives. And I'm multiplying this by 1, 6. I'm going to type this in exactly how this looks into my calculator. And I'm going to see what I get. I grabbed my TI-89, but you know, all my calculators should work the same. So let's see what we get when I do this. A little faint, so I'll bring it up close in that important moment. I've got 0 minus 1, 6 squared times 5, 6. And then I've got for the next probability, 1 minus 1, 6 squared times 1, 6. And my TI-89 does something a little bit weird. It puts that into a fraction. It gave me 5 out of 36. Okay. But if I make that into a decimal, that is approximately a variance of 0.1388 repeating. Okay, so that's a single die roll. I'm trying to understand sort of these base pieces before blowing this thing up. Let's look at a single coin flip. I'll start with the expected value here. So looking at this coin flip, heads and tails, 50% chance of each. The expected number of heads, so I'm going to take 0 heads, happens 50% of the time. 1 head happens 50% of the time. 0 times anything is 0. 1 times that just gives you that piece. So that's 0.50 is your mu. Let's find the variance. Going to take the first x value for this coin flip, 0, minus the center of 0.5. Going to square this. I'm going to multiply this by the probability of 0, also 0.5. A lot of 0.5s in this one, that's okay. My next x value is 1, minus the center is 0.5 again, multiplied by the probability of 0.5. I'm going to type this into my calculator. I'm going to pull out my 84 for this, a little bit easier to read on the screen. And when I did this, I got a variance of 0.25. Now, you may be noticing something about these results. Looking back at P and Q, 1, 6, and 5, 6, there's a way to get 1, 6. It's one of those numbers. And there's a way to get 5 out of 36 doing something with these two values. Should also work for these numbers down here. If you take this 50% and 50%, this P and this Q, there should be a way to get this 0.5. It's one of those numbers. And there should be a way to get this 0.25 by doing something with those two numbers. I'd encourage you to pause the video here and take a guess to see if you could come up with formulas for finding the expected value and the variance using just the letters P and Q. So that way we don't have to do this long process every single time. When you're ready, unpause. I'm going to go through and give you that result now. Okay. You may have noticed this. If you did, awesome. If not, that's okay. This value 1, 6 is coming to you from the value P. I can match that up here as well. Mu there ends up being that probability P. 0 times Q is going to cancel out the Q. 1 times the P is going to leave you with the letter P. If you do a little bit of algebra, you can also see that your variance ends up being a combination of P times Q. 5 times 1 gives you 5. 6 times 6 gives you 36. That's pretty handy. I can check that here as well. 0.5 times 0.5, that's like 5 times 5. That's giving me this 25 here. This is a nice enough takeaway that I'm going to write this on the next page as a formula, but now I have a base that I can blow up to look at more than just one trial. I have a formula for the average and variance for one thing. So if you're dealing with a Bernoulli trial, the expected value is your success rate, P, and your variance is your success rate times your failure rate. So for example, suppose X is Bernoulli and P is 0.2. Calculate the expected value and the variance. Well, you can make a table. You have 0 or 1 success. You can list your probabilities. You have a 20% success rate and an 80% failure rate. And you could use the longer formulas here to find the expected value and the variance. Or you can use the shortcut to go, okay, this is P, this is Q. The expected value of this Bernoulli trial, something where there's a 20% chance of winning and an 80% chance of failing, is just your P. or your 20%. Your variance is going to be your success rate times your failure rate. 2 times 8 gives me something like 16. Done. So I've exchanged so far this longer formula for finding expected value and variance to these really quick short ones. Again, this only works for n equals 1 trial. So a single coin flip, a single die roll, a single game where there's a 20% chance of winning. But that's not what we want long term. We want to be able to look at any number of trials. So by, again, meaning 2 options, success and failure. So we have a fixed probability of success, P, a fixed probability of failure, Q. Nomial meaning many trials. So fixed probability of success, failure. It is either a success or a failure as you go. I want to have independence between my trials. The backup for this is the 10% rule. And now, instead of just 1, I want to consider n of these things. When I'm dealing with these, I don't care if that win is the first win or the last win. When I'm rolling the 2 dice here, if I want a 6, I don't care if I get a 6 on the second die or if I get a 6 on the first die. I'm just trying to get the outcome 6. So if you have all of these things, we consider it to be binomial. And I have binomials are n of the Bernoullis. Here's what I mean by this. If each of these coin flips, dice rolls has an expected value of P, then if I'm looking at n of them, I expect an expected value of n times P. If the variance for a single one is PQ and I have n of these PQs, the variance is going to be NPQ. This looks pretty trivial, but let me show what this is really doing, because this is a small formula, but there's a lot going on behind the scenes. So for binomials, success, failure, multiple trials, the expected value for X is number of trials times our success rate. Our variance is number of trials times our success rate times our failure rate. And our standard deviation is going to be the square root of that variance. For example, we already saw something that was a binomial when we were looking at these 2 die rolls. So let's consider that binomial. And a little bit of notation here. We rolled a die twice, and we're looking at the number of 6. I would say this variable X is binomial, a success or a failure. I'm rolling the dice 2 times. So this first number will be the number of trials. This is my n. And the second value will be my probability of success, P. So that's just a little bit of special notation for binomials. We'll see this showing up as we go through problems. Let's list what's really going on, though. 2 trials, 1/6 for my success rate, 5/6 for my failure rate. And I want to find the expected value and variance. Now, earlier to do this, I had to draw my entire tree, find the probabilities, and use these longer formulas. Now I'm going to find the expected value instead by just doing n times p, and let's see what we get. I have 2 is the number of trials. 1/6 is my probability of success. I multiply these together, and I get an expected value of 0.333 repeating. Again, going back to this first page, when I did all of this work earlier, I got 0.333 for my expected value as well, but I had to do a lot of setup to get that number. Now, 1 second, boom, type it in my calculator, I know what should happen. If I want the variance, shortcut formula says take n, number of trials, p, my success rate, and q, my failure rate, and multiply them together. So I have 2 times 1/6 times 5/6. I'm going to type that into a calculator and see what I get. I could have just multiplied that last number by 5/6, but I'm typing it out. 0.277 repeating. Doing this the long way earlier, 277 repeating. I think I prefer just doing this quick step instead. To get the standard deviation, I'd look at the square root of n times p times q. In other words, if I wanted that standard deviation, I'd just take the square root of variance. And let's see what this gives us. .527 compared to my earlier standard deviation of 527. So now I have the raw data way of doing it, the theory way of doing it, and I'm adding to that a shortcut way of coming up with the same result that takes me seconds instead of minutes. And in some extreme situations, I probably wouldn't even want to think about that tree. So let's look at example 8. We anticipate that 6% of people that show up for a blood drive have O negative blood type. This is a really sought after blood type. Let X be the number of O negative people in a group of 100 that showed up to give blood. I want the expected value and the variance. If you're following along at home, I would encourage you to pause the video here to see if you could come up with that expected value and standard deviation before we go through it together. Okay, let's try it out together. This is binomial because they're either O negative or they're not O negative. Looking at a group of 100 individuals, and the success rate is 6% for being O negative. So this is binomial, it's success or failure. The number of trials here is 100. And my probability of success is 6%. So just showing you that notation again in case you run into that while you're going through things. Listing it out again, 100 trials, 6% success rate. If there's a 6% success rate, that means there's a 94% failure rate. These are complements, they add up to 100%. 6% are O negative, 94% are not O negative. I want the expected value. Shortcut way, I'm not drawing a tree with 100 set of branches. That's ridiculous, that'd be way too big. I'm just gonna do my N times my P. So out of 100 people, 100 times 0.06 gives me 6. I expect 6 people out of 100, that's 6%, that makes sense where that 6 is coming from, to be O negative. Now, sometimes I might get 5, sometimes I might get 8 or 7. So this is an average. Let's see how this average varies by doing n times p times q. I have 100 times 0.6 times 9.4. Typing that into a calculator. I get a variance of 5.64. Variance units are super weird though, because variance would be something like people squared. All my units got squared on me. So if I wanted some units that actually made sense, I would have to look at the standard deviation, the square root of this. So let's look at the standard deviation of that and see what we get. .375 or so. Units, people. So I expect 6 out of 100 people to be O negative, this sought after blood type, give or take 2.375. Here's how I use these things together. Someone might wonder, okay, well, how likely is it that I get 11 people out of the 100 to be O negative? Because maybe there's an emergency and I need this blood right away, and I'm hoping I can get it from this drive. Let's calculate this z-score to see if this is usual or unusual, to see if we would be surprised. Because in general, I'm going to be surprised about something if it is unusual. So we're going to calculate the z-score by taking the value that this question is about, subtract the average or the center, that's our expected value, and dividing this by our standard deviation. I'm wondering what's going on with 11. I'm comparing this to my expected value or my center of 6. And I'm going to divide this by my standard deviation, which looks at the spread of 2.375. Let's see what we get when we do this. When I'm typing this into my calculator, I want to make sure that I have parentheses around the top. So I have 11 minus 6 divided by 2.375. When I do this, I get a result of 2.11 or so. Since our z-score is not between -2 and 2, our results of x equals 11 people being O negative would be unusual. It is more than 2 standard deviations away. And if the thing is unusual, if I was hoping to see this and it actually happened, I should be delighted because I'm surprised by something that's unusual. So just by the expected value in the standard deviation, I can already start to check if things look likely or not likely. I can actually take this one step further using technology though, because GeoGebra can be used to calculate all of the probabilities. So while I don't want to draw a tree with 100 set of branches, GeoGebra is going to do that instantaneously for me. Let's look at the process that GeoGebra uses to calculate these probabilities. I'm going to show you the steps first, and then we're going to calculate some things out. I want to calculate the probability of 11 or more out of 100 people being O negative. I also want to be able to calculate the thing, something like getting 2 6s and 2 rolls. So we've done this for small n using trees. If it gets too big, we use GeoGebra. These are the steps. Step 1, go into GeoGebra. You could go to geogebra.org, go into really any of the options. I think Classic works the nicest. Here's a link to it. Choose the option for probability. And there's going to be a drop-down menu. Inside of that menu, choose the option that says binomial. Let me show you these steps so far. I'm going to go into GeoGebra. I'm going to look at the Classic. Into the option for probability. And in this drop-down menu where it says normal, I'm going to choose the option that says binomial. It wants to know which binomial. So it wants to know the n and the p. So this is matching up with this kind of notation that we had on the previous page. It wants to know the number of trials and your success rate. So in this first spot, type in the total number of trials that you have, for example, 100. In the probability, type in your success rate. Maybe we're looking at 6%. And now all the probabilities for 0 out of 100 successes, all the way to 100 out of 100 successes, show up in this table to the right. So if I want to know the probability of having exactly 5 people out of 100 that were O negative, I would take the probability for 5. So there's a 16% chance of exactly 5. If I want to know the probability of 11 individuals, I could find the 11 right here. There's a 2% chance. You may notice on the bottom, there are some of these options that if you click them, they'll shade in certain directions. If you choose this option here, it will shade it to the left. So if you're looking at less, that's the option you want. If you're looking at this option here, this will shade it to the right. So if you're looking for more than a number, that's the option you want. So for example, if I wanted the probability of 11 or more successes here, I'm in GeoGebra, I shade it to the right from 11, there is a 3.76% chance of having 11 or more people out of 100 that are O negative. That's pretty rare. It looks like it happens less than 5% of the time. Let's verify that this works for another one of our results that we were doing earlier. Namely, we made this big tree, and I want to know if I can use this in place of that. So let's say I am trying out another one of these just to see how it works. 2 dice rolls, 1 6 for the probability. And I just want to verify that this thing works the way that I think it should. So I'm going to go into my n, number of trials, 2. My probability of success, 1 out of 6. And it takes fractions. And when I do this, it gives me probabilities of 2.7%, looking good so far, 27.7%, and 69.4%. Not only have I come up with shortcuts to replace the expected value, variance, and standard deviations, now with just 3 or 4 clicks, I don't have to do trees for these really nice types of problems. I'm going to try out another one of these with you. I'm looking at example 9. So suppose that I'm looking at 20 donors that come in to donate blood, and 6% of them are this universal donor type O negative. And I'm wondering, what's the probability that exactly 2 are O negative? What's the probability 10 or less are O negative? What's the probability 14 or more are O negative? So I'm going to do these first 3 using GeoGebra. Let's try it out. For number of trials inside of binomial here, I'm dealing with 20. My success rate is 6%. And for exactly 2, I'm going to want just the block for 2 shaded in. So I have 20 for my n. For my p here, I'm going to have 0.06. And then I want equal to the block of 2. That's just that one number there of 0.2246. There's a 22% chance that exactly 2 people out of 20 will be O negative. Let's say I'm looking at 10 or less. I'm going to click the left button, the less button. I'm going to type in the number 10 and verify it shades everything from 10 or less here. Great. It's adding up all of these blocks. You can physically add them together. And it's so close to 100% that GeoGebra just calls it 1. Let's look at 14 or more. This is going to add up the blocks to the right, so 14 and higher. That's almost impossible. It's such a small probability that GeoGebra calls this 0. Technically, it's just a tiny bit bigger than 0. It's not impossible. It's just really unlikely, so we'd call that 0 plus. Technically, it's not 100%. It's like 0.9999 repeating. You would call that 1 minus. So just so you're aware, if you see 0 plus and 1 minus, that means it's really, really close to 0% and 100% respectively. Let's look at 3 more examples. Parts to example 10. So suppose that 75% of students drive to campus, and we sample 10 independent students. We want to look at success and failure for these 10 individuals, and there's a 75% chance that they drive. So inside of GeoGebra for the n, looking at 10 trials, probability, 75%. The probability that no one drives, 0 drive. So I'm going to choose the block for 0. Really close to 0%, I would call that 0 plus. Everyone drives, that's all 10 of them. That's 0.0563. I don't have to draw a tree with 10 sets of branches with 75 and 25. It spits out the numbers. I like that. At least 1. At least 1 means 1 or more. So I'm going to shade to the right, make sure I'm highlighting all the blocks for 1 and bigger. GeoGebra says this is almost 100% when you add these numbers together. So it's going to be just a tiny bit less than 100%. It's going to be like 0.99999, pretty close to 1. Whenever you have a situation with a fixed number of trials, fixed probabilities for P and Q, and your order doesn't matter. Let me explain what I mean by that. You can use binomials. So in a problem like this, where I say exactly 2 people have O negative, I don't care if those are the first 2 people out of the 20, if it's like the first person and the 17th person, I just want 2 anywhere in that list. Now, sometimes it's going to give you problems where it says something really specific, like the first O negative person is the 3rd person. If you're in a situation like this, where it's giving you a really specific order, you're going to have to go back to some of your old techniques. So when order matters, list it out and multiply. So for example, the first person to be O negative is the third person. This specific order would mean that the first person is not O negative, failure. The second person is not O negative, failure. But the third person is success. So if you could write it out as a specific letter of events, you don't need to use GeoGebra, you just need to multiply those probabilities. The probability of not being O negative is 94%. Probability of not being O negative is 94%. The probability of being O negative is 6%. I'm going to type that into my calculator to see what I get. So while this binomial distribution is really fast, make sure that you're trying to pay attention to situations where order does matter, because I still have to use that same technique that I had from probability. Other thing that you need to watch out for is be careful about changing probabilities. For example, this problem says 3 people do not drive to campus out of the 10. I don't care if those are the first 3 or the last 3, so order doesn't matter here. That's pretty promising. But while all these other problems are talking about driving, this one is talking about not driving. So I don't want to consider a success rate of 75% here. Not driving tells me I should be typing in 25%. 75 drive, 25 don't. So if I'm doing this last one, 3 out of 10 don't drive, I would want to do it out of 10 trials, 25% for my success rate, and I want 3 of them to be non-drivers. So 25%. I'm finding the block for 3, and that gives me 25.03%. You might have other ways to do this problem that don't involve changing those probabilities. Great. If you're still getting the same answer, I encourage you to go for it. This is just a note to be really careful with your setup as you're going through these problems. I would encourage you to continue to practice both the shortcuts for finding the expected value, as well as using GeoGebra to find these probabilities. It's faster than using trees, but it still takes a while to get used to it. I hope that gives you a first step into that direction, though.